Welcome to our deep dive into the kinetic theory of gases. This fascinating chapter explores how the microscopic motion of molecules explains the macroscopic properties of gases. From the pressure inside a balloon to the temperature you feel on a hot day, the kinetic theory provides a powerful framework for understanding the behavior of gases. In this video, we'll break down the key assumptions, derive important equations, and connect theory to real-world phenomena. Let's begin our journey by understanding the foundational assumptions that set the stage for everything else in kinetic theory. Kinetic theory of gases is built on several key assumptions. First, gases consist of a large number of tiny particles or molecules that are in constant random motion. These molecules are so small compared to the distances between them that their own volume is negligible. Collisions between molecules and with the walls of the container are perfectly elastic, meaning there's no loss of kinetic energy. Additionally, there are no attractive or repulsive forces between molecules except during collisions. These assumptions simplify the complex behavior of gases, allowing us to derive meaningful equations and predictions. Now let's derive the expression for the pressure exerted by a gas. Imagine a container filled with gas molecules bouncing around. When these molecules collide with the walls, they exert a force. By considering the change in momentum during these collisions and the frequency of impacts, we can mathematically show that the pressure is proportional to the average kinetic energy of the molecules and the number of molecules per unit volume. This derivation links the microscopic world of molecules to the macroscopic property of pressure that we measure. Have you ever wondered how far a gas molecule travels before bumping into another? This average distance is called the mean free path. In a gas, molecules are constantly moving and colliding. The mean free path depends on factors like the size of the molecules and the density of the gas. In low-density gases, molecules travel farther between collisions, while in high-density gases, the mean free path is shorter. Understanding mean free path helps explain properties like diffusion and viscosity in gases. Degrees of freedom refer to the number of independent ways a molecule can move or store energy. For a simple monatomic gas, molecules can move in three directions, x, y, and z, giving 3 degrees of freedom. More complex molecules like diatomic or polyatomic gases can also rotate or vibrate, adding to their degrees of freedom. This concept is crucial for understanding how energy is distributed among molecules and how gases absorb and release heat. Law of equipartition of energy states that, at thermal equilibrium, energy is equally distributed among all available degrees of freedom. For each degree of freedom, a molecule has an average energy of 1/2 kT, where K is the Boltzmann constant and T is the temperature. This law helps us predict the average kinetic energy of molecules and explains why different gases have different heat capacities based on their molecular structure. Let's derive the expression for the average kinetic energy of gas molecules. According to kinetic theory, the average kinetic energy per molecule is directly proportional to the absolute temperature of the gas. Mathematically, it's given by 3/2 kT, where K is the Boltzmann constant. This relationship shows that as temperature increases, the average energy and speed of molecules also increase, explaining why gases expand and move faster when heated. There's a direct relationship between the pressure of a gas and the average kinetic energy of its molecules. By combining the expressions for pressure and kinetic energy, we find that pressure is proportional to the average kinetic energy per unit volume. This connection is fundamental in understanding how microscopic molecular motion leads to the observable property of pressure in gases. Boltzmann constant, denoted as K, is a fundamental constant in physics that relates the average kinetic energy of particles in a gas to the temperature. Its value is approximately 1.38 times 10^3 Jk. The Boltzmann constant appears in many equations in kinetic theory and statistical mechanics, serving as a bridge between the microscopic world of atoms and the macroscopic world of temperature and energy. Root mean square (RMS) speed is a statistical measure of the speed of gas molecules. It's derived from the average of the squares of the molecular speeds and is given by the formula VRMS equals SQRT 3kT/m, where m is the mass of a molecule. The RMS speed provides insight into how fast molecules are moving on average and is crucial for understanding gas pressure and temperature relationships. Among all the molecules in a gas, the most probable speed is the speed at which the largest number of molecules are moving. It's slightly less than the RMS speed and is given by VMP equals SQRT 2kT/m. This value is important in statistical mechanics and helps describe the distribution of molecular speeds in a gas sample. Average speed of gas molecules is another useful measure, calculated as the mean of all molecular speeds. It's given by VAVG equals SQRT 8kT/pm. While it's higher than the most probable speed but lower than the RMS speed, knowing the average speed helps in understanding diffusion and other transport properties of gases. Three important speeds in kinetic theory, most probable speed, average speed, and RMS speed, are related but not equal. Their mathematical relationship is VMP VAVG VRMS. This hierarchy arises from the statistical distribution of molecular speeds and helps us understand the range of molecular motion in a gas sample. Maxwell's distribution law describes how the speeds of molecules in a gas are distributed at a given temperature. It shows that most molecules have speeds close to the most probable speed, with fewer molecules moving much faster or slower. The distribution broadens as temperature increases, meaning there's a wider range of molecular speeds at higher temperatures. Specific heat is the amount of heat required to raise the temperature of a unit mass of a substance by 1 degree. In gases, specific heat depends on the degrees of freedom available to the molecules. The kinetic theory explains why monoatomic, diatomic, and polyatomic gases have different specific heats based on how energy is partitioned among translational, rotational, and vibrational motions. For gases, Cp is the specific heat at constant pressure and Cv is the specific heat at constant volume. The kinetic theory provides a simple relation, Cp/Cv equals R, where R is the universal gas constant. This relationship is fundamental in thermodynamics and helps in calculating the work done by gases during expansion or compression. Adiabatic index, also known as gamma, is the ratio of Cp to Cv. It determines how a gas behaves during adiabatic processes where no heat is exchanged with the surroundings. The value of gamma depends on the degrees of freedom of the gas molecules and is crucial for understanding sound speed in gases and thermodynamic cycles. Brownian motion refers to the random, zigzag movement of tiny particles suspended in a fluid, like pollen grains in water. This phenomenon is direct evidence of the kinetic theory, as it results from countless collisions with fast-moving molecules of the fluid. Brownian motion helped confirm the existence of atoms and molecules, providing a bridge between theory and observation. Fusion is the process by which gas molecules spread from regions of high concentration to low concentration. This occurs because molecules are in constant random motion, colliding and moving in all directions. The rate of diffusion depends on factors like temperature, molecular mass, and the mean free path. Diffusion explains how smells travel through the air and how gases mix naturally. Fusion is the process by which gas molecules escape through a tiny hole into a vacuum. The rate of effusion depends on the speed of the molecules and the size of the hole. Lighter molecules effuse faster than heavier ones, a principle used in separating isotopes and in various industrial applications. Effusion provides another window into the behavior of gases at the molecular level. Kinetic theory of gases is a cornerstone of modern physics. It connects the microscopic world of atoms and molecules to the macroscopic properties we observe, like pressure, temperature, and volume. This theory not only explains everyday phenomena but also underpins advances in chemistry, engineering, and even biology. Understanding kinetic theory is essential for anyone studying science or engineering. Zoom into the microscopic level and visualize a gas as a swarm of rapidly moving molecules. Each molecule moves independently, colliding with others and with the walls of the container. These collisions are the source of gas pressure and are responsible for the transfer of energy throughout the gas. This microscopic perspective helps us appreciate the random and dynamic nature of gases. In kinetic theory, collisions between gas molecules are considered perfectly elastic. This means that when two molecules collide, they bounce off each other without losing any kinetic energy. Elastic collisions ensure that the total energy in the system remains constant, which is a key assumption for deriving the laws of kinetic theory. Another important assumption is that the volume of individual gas molecules is negligible compared to the total volume of the gas. This allows us to treat gases as if they are made up of point particles, simplifying calculations and making the mathematics of kinetic theory more manageable. Except during collisions, gas molecules are assumed to exert no attractive or repulsive forces on each other. This means that, under normal conditions, molecules move independently of one another. This assumption breaks down at high pressures or low temperatures, where real gases deviate from ideal behavior. While the assumptions of kinetic theory are idealizations, they provide remarkably accurate predictions for many real-world gases under ordinary conditions. Deviations occur at very high pressures or very low temperatures, but for most practical purposes, the kinetic theory gives us a powerful tool for understanding and predicting gas behavior. Temperature is a measure of the average kinetic energy of the molecules in a substance. In gases, higher temperatures mean faster molecular motion. This increase in speed leads to more frequent and forceful collisions with the walls of the container, raising the pressure if the volume is held constant. According to kinetic theory, if the volume of a gas is decreased while keeping temperature constant, the molecules have less space to move. This results in more frequent collisions with the container walls, increasing the pressure. This relationship is described by Boyle's law, which states that pressure and volume are inversely proportional for a fixed amount of gas at constant temperature. Avogadro's hypothesis states that equal volumes of all gases at the same temperature and pressure contain the same number of molecules. This principle is fundamental to understanding gas laws and is supported by kinetic theory, which treats all gas molecules as essentially identical in their behavior. While kinetic theory describes ideal gases, real gases sometimes behave differently, especially at high pressures or low temperatures. In these conditions, intermolecular forces and the finite size of molecules become significant. Understanding the differences between ideal and real gases helps scientists design better experiments and industrial processes. The principles of kinetic theory are at work all around us. From the inflation of a tire to the fizz in a soda can, the motion of gas molecules explains many everyday phenomena. Even the way we breathe and how our lungs exchange gases relies on the principles of diffusion and pressure described by kinetic theory. The familiar gas laws, Boyle's, Charles's, and Avogadro's, can all be derived from the assumptions of kinetic theory. These laws describe how gases respond to changes in pressure, volume, and temperature, and are essential for understanding everything from weather patterns to chemical reactions. When gases are heated, energy is transferred to the molecules, increasing their speed. This energy transfer can occur through conduction, convection, or radiation. The kinetic theory explains how energy is distributed among molecules and how it leads to changes in temperature and pressure. The mass of gas molecules affects their speed at a given temperature. Lighter molecules move faster than heavier ones. This explains why hydrogen, the lightest gas, diffuses and effuses more rapidly than heavier gases like oxygen or nitrogen. In kinetic theory, temperature is always measured on the absolute, or Kelvin, scale. This is because the kinetic energy of molecules is directly proportional to the absolute temperature. 0 Kelvin, or absolute zero, represents the point where molecular motion theoretically stops. Kinetic theory isn't just academic, it has real-world applications in technology. It's used in designing engines, refrigerators, and even spacecraft. Understanding how gases behave under different conditions allows engineers to optimize performance and safety in countless devices. Kinetic theory is fundamentally statistical. It doesn't track individual molecules but instead uses averages and distributions to predict the behavior of large numbers of particles. This approach is powerful because it allows us to make accurate predictions even when dealing with trillions of molecules. While kinetic theory explains many properties of gases, it has its limitations. It assumes ideal behavior and neglects intermolecular forces and molecular volume. At high pressures and low temperatures, real gases deviate from predictions, requiring more advanced models like the van der Waals equation. Kinetic theory of gases was developed in the 19th century by scientists like James Clerk Maxwell and Ludwig Boltzmann. Their work laid the foundation for statistical mechanics and revolutionized our understanding of matter at the atomic level. Today, their insights continue to shape modern physics and chemistry. Experiments like the observation of Brownian motion, measurement of gas diffusion rates, and the study of effusion have all provided strong evidence for the kinetic theory. These experiments confirm the predictions made by the theory and demonstrate the reality of molecular motion. Kinetic theory of gases has had a profound impact on modern science. It's the basis for fields like thermodynamics, statistical mechanics, and even quantum mechanics. Its concepts are used in research ranging from atmospheric science to nanotechnology, making it one of the most influential theories in physics. Let's recap what we've learned. The kinetic theory of gases explains the behavior of gases using simple assumptions about molecular motion. It connects microscopic properties to macroscopic observations, predicts gas laws, and explains phenomena like diffusion, effusion, and Brownian motion. While it has limitations, its insights are foundational for science and engineering. If you're interested in exploring more, consider reading about statistical mechanics, thermodynamics, and the history of kinetic theory. These topics build on the concepts we've discussed and open up new avenues for understanding the physical world at both the microscopic and macroscopic levels. Kinetic theory isn't just theoretical, it's used in designing everything from airbags to chemical reactors. Understanding how gases behave under different conditions allows scientists and engineers to solve real-world problems and innovate new technologies. Thank you for joining us on this journey through the kinetic theory of gases. We've explored the assumptions, derived key equations, and connected theory to practical applications. The kinetic theory remains a cornerstone of physics, helping us understand the invisible world of molecules and the visible effects they create. Keep exploring and let curiosity guide your learning.